Just enjoy and listen to, and have a fun of it.
Welcome to the Deep Dive. I'm your guide, Dexter, and we're here to unpack the complexity of modern technology. Just have fun with us here at Story Radio Station.
And I'm Claire. Really glad to be here to add some context. And hey, before we jump in, if you like what we do, please, subscribe, maybe hit that like button and turn on notifications.
Yeah, definitely do that. It helps us keep digging into these topics.
It really does.
So we recently talked about physical AI, robots working out there in the real world. It all sounded pretty exciting, very futuristic.
Right. The potential is huge.
But today, today we need a bit of a reality check.
It's really about this gap. We're seeing industries trying to move super fast from just, digital stuff, DX, they called it, into the full AI transformation, AX.
AX, right. AI transformation.
Yeah.
Driven by all this connectivity, loads of data, smart machines.
Exactly. And the AI itself, the chips, the algorithms, the pace is just staggering.
And then this is the big but. You talk to the engineers, the people actually on the ground trying to make these robots work.
Ah, yes. They paint a rather different picture.
A very different picture. There's this huge disconnect between the speed of AI development and the slow, difficult reality of actually programming and deploying these robots in factories or warehouses.
And that gap, that disconnect, that's really the #1 blocker right now for physical AI truly taking off at scale.
So that's our mission for this deep dive, right? To really pick apart this gap.
Precisely. Because the business goal for putting AI in robots is hitting what they call hard ROI KPI.
Hard ROI KPI. Okay, break that down.
Key performance indicators metrics tied directly to the bottom line. Things you can measure easily in dollars and cents, like cutting labor costs or boosting production output by X%. Real financial targets.
Got it. Measurable money stuff.
Yep. But the current reality, most of these AI robot projects are still really expensive, often custom-built niche solutions, not the general widespread systems we envision.
Okay. So let's unpack why. You said there are 4 big hurdles.
4 main categories, yeah. We'll look at the technical challenges, the platform issues, the regulatory hurdles, and then the economics and talent problems. They kind of feed into each other.
All right, part 1. Let's start with what you call the biggest technical monster. The sim-to-real gap.
Ah, yes, sim-to-real.
So this is where you train an AI perfectly in a computer simulation.
Wow.
It works flawlessly, hits all the marks.
Looks beautiful on the screens.
And then you put that same AI into the actual robot in the real world, and it just fails. What happens?
It often does, yeah. Or maybe worse, it works sometimes, unpredictably. Think of it like a racing game simulator.
Okay.
You practice and practice. You nail the perfect lap in the simulator. Clean track, perfect conditions, virtual car. Then you hop into the real car on a real track.
It's different.
It's really different.
Yeah.
Maybe the track's a bit dusty. Maybe the air is humid today. The tires wear down just a tiny bit faster than the simulation predicted. And suddenly, you're spinning out. Same principle.
So why can't these multi-million-dollar simulations get it right? What are they missing?
Well, the core of it is that the underlying physical models are incomplete. They're good, but not perfect. And the hardest part to model accurately is contact dynamics.
Contact dynamics, you mean? When the robot actually touches something.
Exactly. That incredibly complex, subtle interaction when a robot gripper closes on an object, or an arm pushes something, or even just slides against a surface. The friction, the slight deformation, the micro vibrations, it's almost impossible to simulate perfectly.
Moving the arm through empty space, A to B, that's easy?
Relatively, yes. Trajectory control is pretty well solved, but the moment you need precise interaction with the physical world, that's where the simulation often falls short. And even tiny differences between the sim and reality can cause the robot to make unexpected errors.
Okay, so physics is hard.
Yeah.
But you also mentioned it's a data problem too, right? Something about the images.
Yeah, that's another layer, especially for robots that rely on vision. Let's say the robot sees an object. In the simulation, it's a clean computer graphic, a CG image. In the real world, it's a camera feed.
They might look similar, though.
They might look very similar to us. But to the AI, the underlying meaning, the dynamic context captured in the pixels can be fundamentally different. There's a mismatch.
And that mismatch happens in the AI's internal map. You called it the latent space.
That's the term, yes. Think of the latent space as the AI's internal representation, its understanding of the world based on the data it's seen. If the simulated world and the real world map to different places in this internal space,
then the AI gets confused.
worse than confused. The learned policy, the skill it developed in the simulation, often just collapses. It loses its ability to generalize, to cope with the inevitable variations of the real world. A slight change in lighting, a reflection, a bit of dust, and poof, especially for visual policies.
Wow. Okay, that sounds fragile. So how are researchers trying to fix this latent space thing?
One main approach is called latent space modeling. It's kind of a diagnostic tool.
How does it work, roughly?
You basically take data from both the simulation and the real world, and you try to map them into a single shared latent space. Then you can analyze that shared space.
To see where they line up and where they don't.
Exactly. It helps you quantify the gap, understand where the simulation is failing to represent reality. It helps diagnose if your simulation data is even useful for training a real-world robot, or if it's actually teaching it the wrong things.
Okay, that makes sense. Diagnosis is key. But while they're figuring that out, if these robots can act unpredictably because of this sim-to-real gap, how can anyone trust them?
Ah, you've hit the next big point. Trust.
Which brings us to explainable AI, right? XAI. If the robot drops a $1,000 engine part, or worse, bumps into a person, you need to know why.
Absolutely critical, especially in industry. We're talking about expensive materials, potentially hazardous substances, robots working right alongside people. Safety isn't optional. Trust is paramount. If something goes wrong, you have to be able to trace that decision.
So is XAI the same as that other term, responsible AI? I hear that a lot too.
Good question. They're related, but different. Think of responsible AI as the design philosophy. Building the AI from the ground up with safety, fairness, accountability baked in. It's proactive, done before deployment.
Built-in guardrails.
Right. XAI, on the other hand, is more like the flight recorder. It comes into play after the AI makes a decision, especially a problematic one. It's about understanding how the AI reached that conclusion. Transparency, accountability, fairness, reliability, showing the results, those are the core principles.
So responsible AI is the seatbelt, XAI is the accident investigation report.
That's a decent analogy, yeah.
And if you don't have good XAI, if you can't explain the robot's mistakes, what happens then?
Well, diagnosing the root cause of an error becomes incredibly slow and difficult. Was it the sim-to-real gap, a sensor issue, bad data, a bug in the code?
And if you don't know why it failed?
Then determining legal responsibility becomes murky. Who's liable? The robot maker, the software provider, the factory owner. This uncertainty drives up insurance costs, increases liability risks.
And suddenly, that hard ROI calculation we talked about looks much, much worse.
Exactly. The technical problem, the sim-to-real gap, leads directly to a trust problem, the lack of explainability, which then becomes a...
Good evening, and welcome to the Story Radio Station, where we explore tales from around the world.
It's all connected. Welcome back. So in part one, we saw how technical failures like that sim-to-real gap create trust issues, especially around XAI, and that ultimately hurts the economics, the ROI.
Right. The technical, trust, and money problems are all tangled up.
Now let's move beyond the AI model itself and look at the plumbing, the infrastructure, and the costs involved in making this stuff work on the factory floor.
Okay, so the second big hurdle, the platform problem. You mentioned robotics relies heavily on something called ROS.
ROS, yeah, the Robot Operating System. It's sort of the standard open source framework lots of researchers and even companies use. The newer version, ROS2, was designed specifically for more complex multi-robot systems.
Sounds good in theory. What's the problem?
The problem is ROS2, while powerful, is still struggling to meet the really strict requirements of industrial settings. Things like guaranteed, predictable real-time performance, rock-solid stability, and robust security. It's not quite there yet for prime time in many demanding factories.
Oh, it's hard to work with.
It can be, yeah. Engineers complain about the complexity, needing frequent rebuilds even for minor changes, and many bigger established companies are finding it really tough to move away from the older, simpler ROS1 because they just don't see ROS2 as a reliable enough industrial replacement yet.
And this isn't just an annoyance, right? You mentioned performance issues. How bad is it?
It can be a major bottleneck, especially for real-time control in complex setups. ROS2 uses something called DDS for communication between different parts of the system.
The DDS, okay.
And tests have shown pretty clearly that this communication layer can introduce significant delays, especially as the system gets more complex. There's a sort of rule of thumb emerging from experiments.
Oh, yeah. What's that?
If the number of subscribers, basic components receiving data goes above about 10, the communication latency, the delay, starts to shoot up dramatically.
10. That doesn't sound like very many in a modern factory with sensors, multiple robots talking to each other.
Exactly. In a system with dozens of sensors, cameras, robot arms, all need to coordinate in real time, that kind of communication delay can be catastrophic. It means you have to artificially limit the complexity of your systems just to make the platform keep up.
Okay, wait. So if the software platform, ROS2 in this case, is kind of immature or shaky
Yeah.
for industrial use,
Yeah.
what do companies do? They don't just give up, do they?
Well, no. What often happens is they try to compensate.
How? By throwing money at it.
Pretty much. They compensate with hardware. If the software can't guarantee real-time performance, they're forced to use much more powerful and therefore much more expensive edge computing hardware.
Edge computing.
Yeah.
You mean running the AI processing right there on or near the robot, not in the cloud?
Exactly. Powerful local processors to crunch the AI numbers fast enough to make up for the software limitations. But edge devices have their own constraints, size, heat dissipation. You often can't just stick a big, power-hungry GPU like you have in a data center.
So you need specialized chips, like NPUs or TPUs.
Often, yes. Neural processing units, tensor processing units, specialized, efficient, but also expensive hardware.
Which drives up the overall cost.
Dramatically, it massively inflates the TCO, total cost of ownership. You've got the expensive edge hardware, maybe specialized integration work. It all adds up, and again, it puts the brakes on widespread adoption because it kills the ROI. Immature software leads to expensive hardware.
Okay, technical gaps, platform limitations leading to high costs. What's next? Wall number 3.
Wall number 3 is external, but huge. Global regulation. This isn't just about who has the best tech anymore.
It's a compliance race.
It's absolutely becoming a compliance race, and international safety standards are turning into pretty powerful trade barriers.
How so?
Key standards, like ISO 10218 for traditional industrial robots and ISO 13482 for newer service, robots think logistics or healthcare robots are being updated, revised aggressively, specifically to address the implications of AI.
Because AI behaves differently than old school automation, right?
Right.
It's not deterministic.
Precisely. Old standards assumed robots followed fixed, predictable programs. But AI introduces uncertainty. How do you certify a system as safe when its behavior isn't perfectly predictable? How do you prove it will be safe in all situations?
That sounds like a testing nightmare.
It is. We need entirely new testing methodologies, new evaluation protocols specifically designed for AI's probabilistic nature. And the stakes are high.
Because if your robot doesn't meet these new, evolving ISO standards,
your product might be effectively blocked from major international markets. Failing certification becomes a major trade barrier. So companies and even countries need to be actively involved in developing these standards now or risk getting locked out later.
tech, platform costs, regulations, feels like we're running out of hurdles, but there's more.
Oh, there is. We've reached the final wall, arguably the most fundamental. Money and people.
Even if the tech worked perfectly and the rules were clear.
You still need the budget, and you need the right skills. Let's talk ROI difficulty first.
Right, the return on investment.
Industrial AI is often highly customized. The AI model that works brilliantly for inspecting car parts might be useless for sorting packages or monitoring a steel furnace. You need specialized models, tailored data, custom integration for each industry, sometimes even each factory.
Which means it's expensive to develop and deploy.
Very expensive. And that makes it hard to show that quick, clear, hard ROI, like we saved X dollars by replacing Y workers, that management often wants to see to justify the huge upfront investment and the ongoing complexity.
So maybe companies need to think broader, include the softer benefits.
That's a good point. Highlighting soft ROI is becoming important. Things like reducing accident risks, improving quality control in ways that prevent costly recalls later, making faster, more accurate decisions. These are valuable, even if harder to pin a direct dollar amount on initially. They help build the overall business case.
Makes sense. Okay, so that's the money part. What about the people?
The fusion talent crisis. This is huge.
Fusion talent. Sounds cool. What is it?
It's the need for people who bridge the old and the new. Experts who understand traditional industrial automation, think PLCs, robot programming pendants, the physical mechanics, and are also skilled in modern AI, deep learning, computer vision, simulation, data science.
So someone who's comfortable debugging Python code for a neural network and knows how to troubleshoot a gearbox on the factory floor.
Exactly. That combination is incredibly rare, a true fusion of skills. Universities are trying to adapt, but the supply of people with this specific blend of expertise is lagging way behind industry demand.
And when demand outstrips supply.
Costs go up. Companies end up relying heavily on expensive external consultants and system integrators. This drives up development costs, causes project delays, and, yes, makes the TCO even higher.
It all comes back to cost and time, doesn't it?
It often does. Investing seriously in training programs that teach ROS2 alongside practical, hands-on problem solving, maybe mentored by experienced engineers, that's becoming critical not just for growth, but maybe even for survival in this space. Hashtag tag tag outro.
Wow. Okay, so let's recap. We've got these four massive interconnected challenges slowing down the physical AI revolution. There's the technical gap, that sim-to-real problem.
Making robots unreliable in the real world.
Then the trust and regulatory issues needing XAI to understand failures and meeting tough new ISO safety standards.
Which act as potential trade barriers.
Third, the platform and efficiency problems, ROS2 not being quite ready, forcing companies onto expensive hardware, raising the TCO.
The software immaturity tax, basically.
And finally, the fundamental economics and talent gap, difficulty proving ROI quickly, and the desperate shortage of people with that fusion skill set.
They all feed into each other. But, the flip side is that progress in one area can help ease the pressure elsewhere. Better platforms mean lower hardware costs. Better explainability builds trust and might simplify certification.
So strategic investment seems key. Things like focusing on that latent space modeling you mentioned, designing for responsible AI from the start, pushing ROS2 towards industrial maturity, and really tackling that fusion talent pipeline.
Those are definitely the directions things need to move.
Now, before we wrap up, you usually leave us with something provocative to think about.
I do have one thought, yeah. Consider the ripple effects. What happens if, say, in the next few years, we do make significant breakthroughs in XAI? If AI systems become genuinely explainable, truly reliable, will the regulators, the international standards bodies, just keep refining the existing rules? Or could they pivot? Could they go from creating standards as barriers to actually mandating the use of proven XAI systems for safety reasons?
Mandating it. You mean forcing companies to adopt this level of AI?
Potentially. If explainable AI becomes the demonstrably safest way to operate, maybe regulation flips from being a brake to being an accelerator, forcing universal adoption much faster than the market might have done on its own.
Huh. Regulation as the catalyst for AI deployment, not the obstacle. That's definitely something to chew on.
A future possibility to consider as this whole field evolves.
Indeed. Well, thank you for breaking down that complex reality for us, and thank you all for joining us on this deep dive.
It was a pleasure, and as always, please subscribe, like, and set your alarms. We appreciate your support.